Hi everyone, and we're back to lecture 6 in our Fourier series analysis and Laplace transforms. So we're going to break up this lecture into kind of three main sections. So continuous Fourier transforms, discrete Fourier transforms, and also in discrete Fourier transforms performing basically Fourier transforms on images, and then finally Laplace transforms. So we're going to start off with continuous Fourier transforms. So when do we do a continuous Fourier transform? Well, actually effectively, what is our goal? Our goal is to take a signal that varies in time, and we want to convert that to a frequency spectrum. So we want to work in reciprocal space. So for time, reciprocal space is frequency space. So we want to take that time signal and see what frequencies exist in that signal. So one of the simplest ways to start off is by looking at a signal where we know the algebraic form. We know it is a continuous signal. We know the function that we're working with. So we can perform a continuous Fourier transform on such a signal. And we can kind of see what frequencies develop. So in order to develop that frequency spectrum, we need to calculate our harmonic coefficients, these a sub n, b sub n, those values. And then we also have to figure out the period of our signal. One of the common misconceptions of Fourier transforms is that you can only work with Fourier transforms if your signal is periodic. That is not the case. You can work and actually do Fourier transforms on aperiodic signals as well. And then again, C sub n, we're going to take our harmonic coefficients, which is denoted by this little sub n, and n is going to be our, basically the order of our harmonic coefficients. So when n equals 1, that is going to be our first harmonic coefficients. And so we're going to take the magnitude of both those harmonic coefficients and we're going to plot it as a function of frequency. And essentially what we're going to see here is that we're going to plot our frequency as basically integer values times our fundamental frequency. So your fundamental frequency, or your delta f, is going to be equal to 1 over your period. That is the lowest frequency in your signal. And basically what we're going to do is we're going to see, well, that fundamental frequency correlates with first harmonic, so C sub 1. So C sub 1 here. Second harmonic will be 2 times delta f, and that'll be C sub 2, and so on and so forth. So this is a scary looking equation, but it should not scare you. So let's go ahead and let's kind of take a peek at how we can do this manually first, using these expressions, and then how can we do the same thing with our basically Mathematica notation. So I can take the signal. I see it's just a square wave, so 10 until basically pi, and then 20. So I have two piecewise functions. My period is 2 pi, and I can calculate my a sub naught, my a sub n values, and then I can calculate my b sub n values, and I can see what are my harmonic coefficient values as I change my harmonic coefficients. So you see here, a sub n, they're all 0, b sub n here, and then now I could take this function, I could take these values and I could plot my fundamental frequency here as a function of these harmonic coefficients, or the magnitude of these harmonic coefficients. And this is my frequency spectrum. So you can see here, 1 over 2 pi is going to be this value here. And so we can see this is my first harmonic. So this is delta f. This is 2 delta f, 3 delta f. Each of these values is correlated with my second harmonic value. So if I look at these values here, we can take those out. We can see this is associated with the first harmonic, second harmonic 0, then third harmonic, fourth harmonic, et cetera, et cetera, et cetera, et cetera. And you can see that that matches well with the values that we see here. So we can plot for a continuous Fourier transform all the way to infinity. So, and we can also plot and actually develop basically our Fourier series, which is going to be essentially the sum of those sines and cosines and these harmonic coefficients as a function of time. So if you show, and you can see here, if we include 10 harmonics, our blue is our Fourier series approximation of our real signal red. And if we increase the number of harmonics to 50, we get a better and better and better signal. So that's how we do it kind of the old-fashioned way. The next time, we're going to see how we can do this a little bit more efficiently in Mathematica. All right, thanks. I'll see you next time. Bye.